We are live. I think if you guys can hear me, see me, if all of that, technological stuff is working, just drop in the chat, maybe a 1 through 5 as to how you're feeling about AP Chem, how everything's going so far. Just want to make sure you guys can hear me and see where we're at in terms of, AP Chem. So I'll just hang on a minute, wait for a couple more people to kind of shuffle in. I know we kind of got a smaller crowd tonight. Kind of hang out for a few minutes. Tonight we're just going to be going over Unit 3. So it goes through things like intermolecular forces and solids and gases and really a lot of the stuff involving gases, which is really important to your AP exam. And then a couple other kind of miscellaneous topics like solutions and other little things. So I think maybe we'll hang out for like another minute or two, let people shuffle in if they want to. And if not, we'll just jump right in. All right, guess we'll just jump right into it. Let me just share my screen here. There we go. All right. So first things first, be sure to follow Fiveable on all the social media things, Twitter, Instagram, YouTube, all that jazz. All right, so here's a little outline of what we're really going to be going over. The first thing we're going to be doing is intermolecular forces, which is kind of the whole branch off point for this entire unit, right? Everything that we're really going to be talking to, you can kind of connect back to intermolecular forces. So it's a really important topic, not just for this unit, but for the AP exam as a whole. It's really something that they love to ask you about because they're relatively simple, but if you don't know them, you really don't know them. So it's something that's really important to understand involving the AP exam. Then we're going to go into solids, liquids, and gases, and more of the in-depth things regarding them. So, how they interact, how they act, the different types of solids, stuff like that. Then the ideal gas law and kinetic molecular theory, which are all things involving gases. And we're also going to be talking about deviation from the ideal gas law. Then we're going to be talking about solutions and solubility and mixtures. And then finally, we're going to end it off with a couple little things involving light and how things like absorption work, which we'll get into later with the Beer-Lambert law. So let's just jump right into it. So as I said, the first thing we're going to be talking about is our intermolecular forces, right? And these are really important to your AP exam, right? They love to ask these on just any type of free response question because they could easily just shove in, what intermolecular forces are found in this, and boom, there's a whole part right there. And so it's really something that is important to know for your AP exam. So really, intermolecular forces are just, simply put, attractive forces between molecules. So if you have a molecule here, they feel some sort of attraction, that's an intermolecular force, right? And there are 4 main types of intermolecular forces, right? So there are ion-ion forces, Ion-Dipole Forces, Dipole-Dipole Forces, and London dispersion forces. And we'll go through each 4 of these in detail. And then the ones with dipole, and London dispersions, those are called van der Waals forces. You don't really need to know that, but it's kind of just something that if they do refer to it, that's what they're referring to. So the first type of intermolecular force that we're going to be looking at tonight are ion-ion forces. They're pretty much the simplest, and you've seen them before, right? They're basically just ionic bonds. They're attraction between oppositely charged ions, and they're the strongest intermolecular force. Right, you got a positive ion here, a negative ion here, opposite charges, they, opposites attract, and so they're held together by the electromagnetic force of opposing charges. So the reason that they're the strongest is because rather than being held by something like polarity, where they're kind of partial charges, or other types of forces, with ion-ion forces, they're straight positive-negative charges, right? And they're held together proportionally to Coulomb's law, which we learned about in the last unit, right? That is based off of the distance of the ions and the charges of themselves that leads to a stronger interaction. So two ions will have the strongest intermolecular force. And that kind of explains why when you see things like salt, right, like table salt, it's so hard to melt. Because if you want to break those ion-ion bonds, you're going to have to put in a lot of energy. Right, so that's why salt has a boiling point of like 1,000 degrees Celsius, because you need a ton of energy to break those intermolecular forces and turn it into liquid salt. All right, so the next one, we're going to be talking about our ion-dipole forces. And again, these you've probably seen in your class before, right? They're just attraction between an ion and a polar molecule. So we see the most common example, and really the only example that I can think of, would be something dissolving in water, right? So you see we have these polar waters, and we'll go into polarity a little bit later, surrounding the positive and negative ions, right? So we have an interaction between the negatively charged or positively charged ion and the positive or negative sides of the polar molecule in this water. So we see here we have water, right? We have a negative side, and so it's attracted to that positive ion, and we see the water surround it, right, with the negative side facing the sodium. Similarly, when we look at a negative chloride ion, we see that the waters are flipped, right, because now the positive end is attracted to the negative ion. And so that's why, you've probably seen a picture of something like that before. That's where that actually comes from the ion-dipole forces between some sort of ionic compound and water or another polar solvent, typically. All right, so the next one, and arguably the most important one, are what are called dipole-dipole forces. So dipole-dipole forces are really just, simply put, attractions between polar molecules. So, right, so you see this polar molecule here. We know that because it's polar, it will have a positive end and a negative end, right? And so because of this, when we have multiple molecules, floating around together, the negative end of that molecule, in this case the chlorine, right, will be attracted to the positive end of the other, in this case hydrogen. We see the same thing happen with iodine monochloride, I think that's called, right? We see the negative chloride be attracted to the positive iodine in this case. So that's really how dipole-dipole forces work, and they're really common, and they will be found in literally any polar substance, right? So ammonia, water, hydrochloric acid, hydrofluoric acid, chloromethane, any sort of polar molecule will have dipole-dipole forces, right? And they're relatively strong. They're not in. It really depends on the molecule as to how strong they are. But there is a form of dipole-dipole forces called hydrogen bonding, and hydrogen bonding, they're the strongest form of dipole-dipole forces, right? So really, they're the same. Hydrogen bonding tends to really trip up students, right? And the reason for this is that they think that it's different from dipole-dipole forces, when in reality, these are the exact same as dipole-dipole forces. However, they're stronger because they're between hydrogen and a highly electronegative ion, which the AP exam considers nitrogen, oxygen, and fluorine to be the ones that you will see exhibit hydrogen bonding. So we see here with water, right, we have the negative oxygen attracted to the positive hydrogen. So this is just a dipole-dipole force. However, what makes it special is the fact that we have an intermolecular force, a dipole-dipole force, between the hydrogen and the oxygen, making it a hydrogen bond, which is stronger than a normal dipole-dipole force. However, they are the exact same, right? This is the same as this bond, this force from before, except just stronger due to the fact that oxygen and hydrogen will form a hydrogen bond, right? Same thing happens with ammonia, right? If you have two ammonia ions or two ammonia molecules, we see this this nitrogen attracted to the hydrogen because of the polarity of ammonia, and because it's an N bonded attracted to an H, we see again a strong hydrogen bond form. And I know we see a couple people kind of hopping in and out. Have any questions about this? I know I'm moving kind of quickly. Feel free to drop any questions you have whatsoever, even if it's not really super related to this. I'm here for you guys, so if you have any questions whatsoever, feel free to drop them in the chat, and I'll be kind of popping in back and forth from time to time. All right, so then the last type of intermolecular force that we're going to be looking at are what are called London dispersion forces. And there are three types, but I think on the AP exam, I'm fairly certain you can just refer to them as London dispersion forces. And so when we're looking at London dispersion forces, they have to do with non-polar molecules, right? So you might be thinking to yourself, okay, we've got a non-polar molecule, so no forces are felt between the molecules. However, that's false, because of the fact that if we're dealing with a non-polar molecule, we're still going to see that due to just randomness, right, random movement of electrons around this molecule, there are going to be what are called induced dipoles, right? So they're going to be very instantaneous and very weak dipoles found in non-polar molecules. So we see here, for example, that it just for an instant is is pulled over to a negative side and pulled over to a positive side. And so that induces a dipole. So in a perfectly nonpolar situation where we have something like methane, for example, we're going to see incredibly weak induced dipole forces because methane is nonpolar. If we see something like methane mixed with a polar molecule, we're going to see dipole-induced dipole because we see the induced dipoles of that nonpolar molecule interacting with the dipole of a polar molecule. And the same thing can be said for an ion-induced dipole situation, where if you have a positively charged ion, such as we have here, we're going to see that attracted to the negative side of this induced dipole of a nonpolar molecule. It's kind of a very tricky situation to kind of get through your head, and it takes a little bit of practice of looking at. But essentially, induced dipoles are found in every single molecule, whether you're polar, nonpolar, an ion. Induced dipoles will always be found, except for in ionic compounds. I kind of said ion there. If you are, whether you're polar or nonpolar, you're going to feel induced dipoles because of the fact that the random movement of electrons is still going to create some form of a dipole, right? So when we're talking about induced dipoles, you might be wondering, well, how do we measure the strength of these induced dipoles, right? So we use a measure called polarizability, and I know that's kind of a big word, but all it means is just how easy is it to induce a dipole. Basically, how often are we going to see these random movements of electrons causing a dipole situation? So typically, just the rule is that the bigger an atom is, the more polarizable it is, and therefore the stronger the induced dipoles. Right? So for example, if we're looking at iodine and fluorine, right? You look at your periodic table, and you can see, well, iodine is way, 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 way bigger than fluorine, right? And so by that, we can make the conclusion that intermolecular forces within iodine are going to be stronger than that in fluorine, even though they're both going to be induced dipoles. And in fact, if you look at the periodic table and at some charts, you'll see that iodine at standard temperature is solid, whereas fluorine's a gas. So that's why we see differences in intermolecular forces even within nonpolar molecules. It's because of this concept of polarizability, right? It's because of the fact that certain atoms will have better abilities to actually induce a dipole than others. All right, so here's kind of the definitive, right? This is really the thing that people really want. It's the definitive list of just, what are the strongest to the weakest IMF strengths, right? So we see that we have ion, right, all the way at the top, then ion-dipole, then we have hydrogen bonding, and I kind of got to fix this. Then we have, there we go. Then we see hydrogen bonding, right? Then finally we see dipole-dipole forces and London dispersion forces. So that's really the list in order. And some might think to memorize this, but it just kind of makes sense that ions are going to be stronger than dipoles, and that dipoles are going to be stronger than induced dipoles, right? It kind of makes sense logically, but it's really not that hard also to kind of just memorize. And it becomes second nature after doing a couple of practice problems. So for example, here is an example question, right? There aren't going to be many questions that just straight up ask you which has the strongest intermolecular forces. They'll ask you to use the concept of intermolecular forces to answer a question. So for example, this one is, which of the following most likely has the highest melting point, right? So when you think about what a melting point really is you're looking at what is the strongest really to actually, which is the strongest to break those intermolecular forces, right? That's what you want to do in this situation. And so with this question, you want to look at, well, basically, which of these has the strongest intermolecular forces? So the first thing we can do is we can immediately knock out CH4 because of the fact that it's nonpolar, right? Methane is a nonpolar molecule. And you can know that just by drawing out the Lewis dot structure of it, you'll see immediately that it's nonpolar and we can knock it out. With hydrofluoric acid, it is polar. You'll note that. However, when we're looking at B and D, you'll note that both of those are polar and exhibit hydrogen bonding, right? So really, I kind of wrote this question poorly, but it would come down to whatever the strongest intermolecular force is. So for example, if choice B was changed to something like CO2, right? Now the answer would immediately be H2O, right? Because of the fact that carbon dioxide is nonpolar, methane is nonpolar, hydrofluoric acid does not exhibit hydrogen bonding, and D does exhibit hydrogen bonding, which is the strongest intermolecular force that is shown out of these four molecules. And so that's really how you kind of want to look at intermolecular forces. There really aren't going to be many situations where they do ask you, which of the following has the highest intermolecular forces? They would ask something about melting point or boiling point, or something like vapor pressure, which we'll go over later. And using those qualitative aspects in order to extrapolate data using intermolecular forces. Right. So do you guys have any questions on that? I know we kind of blasted right through that, but it is one of the most important concepts in this unit. So I definitely want to make sure you guys really understand it. Would H2O still have a higher melting point than NH3? In terms of the AP test, they wouldn't ask you that because they both have the same intermolecular forces. I can check. I know we know the melting point of water. Right. Let's see. Melting point of H2O is 0 degrees Celsius, right? Whereas NH3 is, water would have a higher melting point than NH3 due to the fact that oxygen is more electronegative than nitrogen, right? So we're going to see stronger intermolecular forces in H2O. We're going to see stronger hydrogen bonding in H2O compared to NH3. Does that make sense? Yeah, sounds good. Right. Really, when you're doing these problems, and really when you're taking the AP test in general, the periodic table is going to be your best friend. I'll drop a quick website that I kept bookmarked actually when I took AP Chem. It's an online periodic table that I'm sure most of you guys have heard of, but it's honestly your best friend when you're doing these types of problems because you can immediately look at it and say, okay, this is clear from just the chart, right? All right, so let's move on to the next topic, right? So I kind of combined two of the key concepts here into one topic. And so that's on solids, liquids, and gases, right? So we all know from elementary school, right, the three main states of matter, right? Solids, liquids, and gases. And we know the main differences, right? If I put a cup of water in front of you, you would know, oh, that's a liquid. In AP Chem, we go a little bit of a step forward and kind of try to describe the behavior of solids, liquids, and gases. So what we're going to be talking about with solids are primarily the main types of solids that we're going to be looking at. So the four main types that I'll be going over tonight and that will be on your AP exam are ionic solids, covalent network solids, molecular solids, and metallic solids, right? And all four of these might sound really intimidating, really difficult, but they all have very distinct characteristics that make sense once you understand how they work, right? So like before, the simplest type to know are just ionic solids, right? So again, with ionic solids, we're going to see ions attracted to each other. And look at almost like a cross-section of an ionic compound, we'll see that they form a lattice, right? A crystal lattice of positive and negative ions in order to reduce repulsion and minimize attraction, right? We see that sodium ion right here, for example, this sodium ion is attracted to 4 different chlorines and vice versa. Chlorine is attracted to a bunch of sodiums. And so we see that because of the strength of these intermolecular forces, we're going to see that an ionic solid is going to be brittle, right? And whenever I think of an ionic solid, I always think of just a bar of pure salt, right? A bar of pure salt is hard. It's rock hard. You have to snap it in half. And so it's brittle, right? And that's because of this tightly packed crystal lattice that's formed between the ions, right? It also has a high melting point, right? As we discussed before, those ionic forces are going to be the strongest type of intermolecular forces. And so it is incredibly difficult to break apart those IMFs. They don't actually conduct electricity in the solid phase. However, when they're dissolved, right, remember electrolytes and non-electrolytes from previous chapters, when an ionic compound is dissolved in water, it's broken up into its ions, right? When you dissolve salt in water, you get sodium ions and chloride ions. You're going to see that we get a solution that conducts electricity due to the presence of these ions, right? So this is pretty simple. Really is the simplest type of solid because it's typically the one most students are most familiar with. right, so moving on to covalent network solids, right? So there are two types. There are connected networks and there are layered networks. So looking at a connected network first, the way I like to think of a connected covalent network solid is just a giant molecule, right? So when we're looking at something like diamond, for example, diamond is pure carbon, right? However, what makes diamond so hard, so rigid, and gives it the properties that it has is the fact that each of these little lines here is actually a covalent bond between carbons, right? So really what a diamond is just one giant mega molecule of carbons all covalently bonded together. So covalent bonds are the strongest type of interaction there are, right? I know we were talking about ion forces. However, covalent bonds are literal bonds, right? They are genuine, tried and true bonds. Whereas with ionic compounds, we're going to see intermolecular forces holding together the ions. With a covalent bond, it is a literal sharing of electrons, bridged ions, bridged atoms, right? Pure connection. And so we see that this is the strongest type of strongest type of solid, right? So with a diamond, for example, you can't break a diamond. It's the literal hardest substance on Earth. Similarly, when we're looking at something like graphite, right? Graphite's the same as diamond. It's pure carbon. What gives it different properties is actually the way it is a solid. So when we're looking at graphite, we see that these are covalently bonded, right? These little lines here are all covalent bonds. However, when we're looking at those covalent bonds, we're not seeing that there's no covalent bond here. We see sheets of covalent bonded layers of carbon connected by London dispersion forces. And remember, London dispersion forces are the weakest type of intermolecular force. So that's why when you put your pencil of graphite on the paper, it just shreds right off the pencil, because of the fact that those London dispersion forces are so weak. So you can break the graphite, right? So the major thing you should take away from covalent network solids is just basically that they're rigid and hard, right? You know, graphite's still rigid. You can only snap it in half. And they do not conduct electricity. There's no way to get those electrons moving, right? Here, they're all rigidly bonded together. Here, they're all rigidly bonded together. And so we are not going to see any sort of conductivity with something like diamond or graphite or coal, right? There's a lot of carbon things with covalent network solids, but we're not going to see conductivity whatsoever. All right, so the third type, this picture might look really similar to what we were talking about before. However, with molecular solids, these aren't actually covalent bonds. These lines between these water molecules are actually intermolecular forces, in this case, hydrogen bonds. And so when we're looking at something like solid water, or just ice, we see that the water molecules aren't held together by any sort of bond, any sort of ionic force, but they're held together by weaker intermolecular forces. So these weaker intermolecular forces give it, they make it softer, and they give it lower melting points, right? So I always like to kind of have an example for these. Molecular solids, I think of ice, right? And you might think, well, ice has a pretty low melting point, right? Because of the fact that these hydrogen bonds happen. Ice will melt in your hand, right? All you got to do is get it to 32 degrees. Whereas something like salt, if you want to melt salt, you got to get it to thousands of degrees because you have to break those intermolecular forces, right? And finally, we have metallic solids, right? So metallic solids are they're just metals, right? But the thing with metals is that you have a delocalization of electrons, right? So you have the positive nuclei of this atom, let's say it's iron or something, right? Some metal, and instead of having electrons here, electrons here, electrons here, we see what's called an electron sea, where electrons are free to move around them. And this is what gives metals its major properties, right? They are the greatest conductors of heat and electricity, right? And that's because these electrons are given free rein, right? So no matter in the solid phase, liquid phase, you're going to have conductivity of heat and electricity, right? That's why we that's why we make like frying pans out of metal, because they conduct that heat so well. Think about if you made a pan out of something like foam, right? Ignoring the fact that it would melt, right? It also wouldn't conduct that heat all that well. Similarly, metals are malleable, right? They're able to be bent, and they're ductile, which means they're able to be bent into wire, right? So things like copper are really great for making wires, which is really convenient because we take a metal which is able to conduct electricity, bend it into wire, and boom, we've got the ability to use electricity. So that's really something important about metallic solids. The final thing with this is just the difference between crystalline and amorphous solids. I'm going to go through this really quick. It's like one little bullet point in the curriculum. Basically, crystalline substances have this nice grid structure. So this is something like, something like diamond, right? Whereas this is an amorphous solid. It doesn't crystal lattice type look to it, right? Something like glass or sodium, or sulfur dioxide, right? Or I think it's sulfur dioxide. I'm not sure, actually. Silicon dioxide. That's what sand is. Right? So that's the difference between a crystalline and an amorphous solid. So finally, I keep saying finally, we're just going to look at the energy of solids, liquids, and gases. And this is something that even if you haven't formally learned it, you kind of know, right? A solid is really rigid, right? So if you want to make it a liquid, you weaken those intermolecular forces and you put in energy into the system, and you get this liquid, right? Then you want to break the intermolecular forces and create a gas by adding more energy, right? You'll get more into this when you start actually looking at things like thermochemistry and thermodynamics. However, it's really something that is kind of something to look at here, where you have to put in energy and break those intermolecular bonds or intermolecular forces. All right. So does anyone have any questions on what we were talking about, just with types of solids or anything to do with that? We'll just kind of hang out a quick second because I know I'm moving kind of quickly. It's just because there's a ton of information in this unit. All right, if you don't have any questions, you guys can still feel free to ask any questions about what I'm going over from the past. I'm just going to keep moving forward. All right, so the next topic that we're going to be talking about is the ideal gas law, right? This is like the big kahuna of gases, right? This is basically going to be applied to, if not every, I'm still in Unit 2 and I'm chilling. Hey, that's great. Yeah, I'm chilling here to learn random stuff. That's awesome, man. You know, it's also when you get to Unit 3, you're going to be killing it, man. You have all this information in your head, and even in the back of your head, you're going to be killing it. Right, so the next thing we're going to be talking about is the ideal gas law, right? So the ideal gas law looks at how we can relate things like the pressure, the volume, and the temperature and the moles of gas together in one really, frankly, a pretty beautiful equation, right? You might not think it's very beautiful, but when you start using it, trust me, it gets really convenient. So in my opinion, and in most people's opinions, the ideal gas law is the most important equation in this course regarding gases. And we're going to be going over variations in the ideal gas law. So we will be going over that. So, right, just to go over what, PV equals nRT actually means, right? So it says that the pressure times the volume is equal to the moles of gas times the gas constant, yes, R, times the temperature. So the thing that actually people tend to mess up with the ideal gas law isn't the math, it's the units. So for example, they might give you this in what are called torr, or milliliters of mercury, and then they might give you this gas constant in atmospheres, right? You have to make sure, and I cannot stress this enough, you have to make sure all of your units are in order, right? We don't really have time tonight to go over specific problems involving the ideal gas law, unless you guys want me to, in which case, drop a question a little bit later. I'll be happy to go through some. But yeah, really, the most important thing is just making sure your units are in order, right? Especially R. R, there are 100 million different values for R. There's 0.08206 liter atmosphere per mole K. I remember, that's I know. There's 8.314 joule per mole K, I think. There are a bunch. Let me see if I can actually find them for you. AP chemistry formula sheet. There's like 5. Really, it's more convenient to actually convert your units and use 0.08206 because that's just the first one they give you. But yeah, they give you it for joules, atmosphere, and torr. So you do have different values to deal with. So if you have to or want to, you could also swap out R. Just the important thing is to make sure that all of your units line up, right? If you have atmospheres for pressure, you got to have atmospheres in your gas constant. If you have liters in your volume, you got to make sure you have liters in your gas constant, right? Kelvin for temperature, always use Kelvin for temperature. You should never be using Celsius when you're dealing with these. Always convert to Kelvin, and to do that, you just add 273 to your Celsius. So that's really the ideal gas law in a nutshell. It's just really an equation that once you get some practice with it and once you learn how to use it, it becomes second nature, right? They can only ask you so many questions involving PV equals nRT, but it's super convenient because then if you get a pressure, a volume, and like a gas constant and temperature, you can immediately find out moles, right? And go from there. So it's a very convenient equation. So the next thing we're going to be talking about is Dalton's law of partial pressures, right? So again, this is a topic that really tends to screw up a lot of students, but really in simple terms, is when you have a mixture of gases, the full pressure is the sum of the partial pressures. So, right, so when we're looking at, if you have a mixture of, let's say, 3 different gases, right, let's call it A, B, and C, the total pressure is just going to be the pressure of A plus the pressure of B plus the pressure of C, right? And you do that so on and so forth for however many gases you have. So really, that's the main idea. And there are other equations that I'm showing you here that involve finding the actual partial pressures, but that's when you're given the total pressure. Really, this XA is a pretty important topic. It's called the mole fraction, right? It's just basically the moles of A, so how many moles do you have of this, divided by the total moles. It's just a matter of finding a percentage of how many moles make up the total. It's fairly simple in terms of the actual formula, right? And these are all, they're given to you, right? So on the AP exam, they give you PV equals nRT. They give you, I ripped these actually directly from the curriculum. So they are going to be given to you, but it's really simple and easy to memorize, especially because you will be applying these pretty heavily. All right. So here are a couple graphs involving gases that you may have to know. There are 2 main gas laws outside of the ideal gas law that you might want to know and that are pretty convenient. Right. So the first one is Charles's law. So what Charles's law talks about is basically the relationship between temperature and volume. Right. So according to this graph, right, as we increase temperature, we increase the volume. Right. Think of this like a hot air balloon. Right. We increase the temperature of the gas expands, blowing up the hot air balloon. Right. And that's why hot air balloons work, because of Charles's law. Similarly, Boyle's law looks at the relationship between volume and pressure, right? So as you compress a gas, as you add more pressure, you are going to decrease the volume, right? At a low pressure, we're going to have a high volume. At a high pressure, we have a low volume, right? So does that make sense? I know these graphs might be a little bit confusing at first, so I'm just going to make sure I get like a thumbs up from a few people, just making sure that y'all are getting this. Right. Perfect. Awesome, right? Yeah, this stuff is pretty cool. I mean, it helps you understand. This is really the chemistry that you really understand the world, right? You look at a hot air balloon and you're like, oh, look at that, Charles's law. And then your entire friend group is like, dude, shut up about chemistry already. Right, so here's another alternative form of Boyle's law. So here's the graph on the left that we just saw before, right? At a high pressure, at a high pressure, right, we're going to see, right. Yes, at a high pressure, right, we're going to see a low volume. At a low pressure, we have a high volume, right? Similarly, if we graph pressure versus 1 over the volume, we get a linear relationship, right? And this is because of the fact that this is an inverse relationship. And so when we invert the volume, we get a linear relationship. We see that at at a high pressure, we had a really low volume. And so at a high pressure, we're going to have a really high inverse of volume. It's really kind of confusing. I still kind of have to wrap my head around it. But just know that if you see this on a test, this is just Boyle's law. This is just Boyle's law. Okay. A linear relationship between pressure and the inverse of volume. So what we can use these gas laws, right? Charles's law, it's Charles's law, Boyle's law, and what's called Gay-Lussac's law, right? Charles law, Boyle's law, and Gay-Lussac's law, which relates temperature to pressure and volume. We what's called the combined gas law, right? I know you're saying, oh my God, not another equation. This one you actually should memorize. I made the dumb mistake of not memorizing it and not remembering to use it and barely managing to get a question right on the AP because of the fact that I understood the ideal gas law. This is something that's incredibly, stupidly useful. It's used basically to just calculate changes when other things are held constant. So this is actually something where I do want to go through a problem with you guys and kind of go step by step through how to actually do a problem. So here, I'm going to pull up this little online whiteboard thing that I've been using for the past couple streams. And then I'm going to, there we go. Where are we going? I have to just get the actual problem into the whiteboard. There we go. Right? So we say that assuming a constant temperature, right? So constant temperature, if a 1 liter container of gas at a pressure of 0.32 atmospheres is constrained to 0.25 liters, what is the new pressure? Right, so we look at we're going to look at the combined gas law, which states that P1 V1 over T1 is equal to P2 V2 over T2, right? However, we know that temperature is constant. So what we can do is just get rid of the temperatures, right? They won't impact what we're looking at here. So what this boils to, Boyle's law, is P1 V1 is equal to P2 V2, right? And so from here, what we want to do is just plug in our values, right? So our original pressure is 0.32, and our original volume is 1 liter, is equal to P2, we don't know, and we know that the new volume is 0.25. Oh, so then all we do is solve for P2 by dividing by 0.25. And then from there, you would just plug into a calculator, right? So that's really the way that you're going to be using the combined gas law. And the one caveat that I really don't like with the combined gas law is that they don't give it to you. Actually, they will not give you the combined gas law on the formula sheet. At least they didn't give it to my class. And so I don't want to say they will give it to yours. So it's something that you really want to memorize. But it kind of makes sense by understanding Boyle's law and Charles's law and Gay-Lussac's law. Right, so let me pull up the slides again. Right, so that kind of brings us to the end of our equations involving gases. Right, so now we're going to be talking about really why does this happen, right? Why does pressure exist? Why do certain laws exist? And that's where what's called kinetic molecular theory comes into play, right? So there are a few assumptions that the kinetic molecular theory makes. So the kinetic molecular theory is a theory that helps describe why gases act the way they do. So the 4 assumptions, and I kind of bolded the important parts, are that gas moves in random directions, that collisions have no energy loss, that they move in straight lines until colliding with the container, and that the average kinetic energy of a sample of gas is proportional to temperature. So let's break those 4 down for just a quick second, right? I kind of threw a bunch of information at you at once. So let's break these down. Right, so gas moves in random directions at relatively large distances. So basically what this says is that when you look at a sample of gas, it's just going shoo, 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 right? We don't have any order really to the actual molecules. We just see them flying every which way in random directions. And we assume that they're at relatively large distances from each other. So we're not going to see them bumping into each other, and we're not going to see interactions between the molecules. Similarly, collisions are perfectly elastic, right? So we see if we have a container and a molecule bumps off of it, we assume that there is no energy loss, right? It's not going to slow down the molecule. We also make the assumption that gases move in straight lines. That kind of makes sense, right? We don't see a gas under the kinetic molecular theory go like this, right? We don't see it go like that, and then boom, right? We just see boom, boom, straight lines. And then the one that I consider the most important is that the average kinetic energy of a sample of gas is proportional to temperature. Essentially, what this means is that as you increase the temperature, your molecules will get more kinetic energy, which means they will move faster. right? And that, again, kind of makes sense. You put energy into the system, and they're going to start moving more and faster, right? And we'll be looking at something, I think it's on the next slide, of what are called Boltzmann diagrams, involving how we look at distributions of gases, right? And their kinetic energies. Right, so we look at gases and kinetic energy. We know the equation kinetic energy is equal to 1/2 mv squared, where v is the velocity. You don't need to apply this on the exam, but it's in the curriculum in terms of understanding it. This is why when you increase the temperature, you get an increase in average kinetic energy, because you're going to increase their velocity, right? And therefore more energy. Or that's why when you increase temperature, you get an increase in speed, because when you put energy into the system, you get an output of velocity, right? So this is really the conclusion from the relationship between kinetic energy and speed, right? So what this diagram shows, it's not actually showing the speeds of any specific molecules. Rather, it is showing the distribution of molecules that are moving at a certain speed. So we see that at this super low speed, not many molecules, right? But if we look at this speed right in the middle, we see that the most number of molecules are at that, right? So this is what we call the most probable speed, right? And there are other speeds like the average speed right here. But really, what you really want to understand is that that this curve does not show the actual speed. It shows the distribution of speed. So if you had something like this, and I'm kind of going to draw this really bad, like this, even though the curve is lower, it's moving faster because we have a higher distribution going a faster speed, right? In the AP exam, Parth, I'm really sorry. That really sucks, actually. We're trying to get our own platform up and running, but right now we're kind of stuck with Crowdcast. So it's kind of, a love-hate relationship. Right, so this is what Maxwell-Boltzmann diagrams show, right? So let's try to look at a practice problem, right? So we see which of the following Boltzmann distributions are at a higher temperature, right? So remember that a higher temperature implies higher kinetic energy. So really what this question is asking is which of the following gases are moving faster? So is it the orange one or is it the green one? And I'll just tell you if you can't really see it that well. This higher one is the orange one, and the lower one is the green one. So Parth says green. Let's see if anyone else has any different answers, or if everyone agrees, right? All right, give it another minute or two. Seems that it has a higher average. Perfect, right? That's perfect. Green is the correct answer, because although we see that there isn't a peak quite like the orange, the green has a higher average, a higher average speed, right? We see that more of the molecules are moving at, it's like 500 something compared to 200 for orange. So that's a typical problem that students make. They see this big peak and they think, woo, high speed. But when you're looking at the axes, you see that this is the number of molecules, or in this case, actually, it's the probability. But yeah, it's the number of molecules, right? P of V, yes, it's the probability of velocity. So basically, yeah, the number of molecules. The higher you are here, the greater probability it is that you're moving at that speed. So yeah, the more molecules there are. That's really how Boltzmann diagrams really work. They're essentially statistical distributions of probability, as opposed to, but it's helpful to think of them as just number of molecules, right? And you'll never be asked to graph one like this. However, there was a question last year, I'll try to find it, where they asked you to draw a Boltzmann diagram after a temperature increase. So that's a question we might want to look at, if I can find it real fast. I'll give us like 10 seconds to try to find it, and if we don't find it, too bad. Yeah, no, I can't find it. But I think it's in 2017. So if you happen to find it, give it a try. It's a really good question for this unit in terms of looking at the Boltzmann distribution. Oh, there it is. I found it. Right. We don't have time to do it, though. So yeah, I'll drop it in here. It is number 1, part B. Do number 2, like BII. a temperature increase, do we make the peak higher and compress the graph? With a temperature increase, you'll see the curve flatten out, right? So actually, let's do this problem, right? Just for the sake of making sure you understand what that means in terms of a temperature increase. So the context of this problem was that the temperature was decreased, actually, I think. We'll have to read the question. But let's take a look, right? No, you're good, Parth. Don't worry about it. That's actually a really good question that you asked, because they very well could ask about two different curves and the differences between them. So it was a really good question. So don't worry about it. All right, so here we see the graph below shows a distribution for the collision energies of reactant molecules at 120 degrees Celsius, right? So it says draw the second curve on the graph that shows the distribution for collision energies of reactant molecules at 30. So you might be thinking, Dylan, what the heck? This isn't gases. However, you can treat it the same way, right? The energy of collisions, can be really said as kinetic energy, right? Or velocity. Whereas, and fraction of collisions, well, that's just the same thing as the number of molecules, right? A higher fraction, so a higher number. So if we want to draw at a lower temperature, right? Excuse me. One sec. I'm trying to find it again. I lost it. There we go. I got it. Right. So if we want to draw it at a lower temperature, we want it to be we want a higher percentage to be at a lower energy. So we're going to see something that looks like this, right? We see a higher percentage at a lower temperature or a lower energy compared to the other, right? And then we're going to see it dip below this function because a lower percentage are at a higher speed. So does that make sense to how you would draw different lowering or highering the temperature? If we made the temperature higher, what we would do is we would actually draw it something like this. It would kind of flatten out, and you would just see a higher proportion at a higher temperature. So does that make sense, Parth? I know that was your question. So lower temperature means less movement. So how can that make more collision? Okay, so this is kind of getting into kinetics, which we'll get into later. But essentially, we're not looking at collisions. We're looking at the energy of collisions, right? And the fraction of collisions, the number of collisions hypothetically would remain the same. And so if we draw this lower temperature, right, like that, let me draw that again. There we go. That looks good, right? We see that they're at a lower temperature, so a lower energy. So we see that a higher fraction of collisions happen at this lower energy compared to when we have a higher temperature. Does that make sense? We're not seeing actually more collisions. We're seeing more collisions take place at a lower energy. We're seeing the same amount of collisions actually take place, according to the Boltzmann diagram. Awesome. All right. And this stream probably, I'm guessing, is going to go above an hour because there are like 13 points in this actual unit, so it's going to take a hot minute to get through. But if you guys have any questions, feel free to stop me, ask me to go through a problem. Right? I'm here for you, as I've said a couple of times. Right? I'm here to help you guys understand the material, not just blast through it as quickly as humanly possible. So I know, Parth, you said you were on Unit 2. If you have a question about Unit 2, be my guest, man. Drop a question. Right, so the next question, I know we had one person who was asking about this, is going to be deviation from the ideal gas law, right? The ideal gas law is actually complete and utter fiction. There's no such thing as an ideal gas. There are gases that are very, very close to an ideal gas. However, an ideal gas actually doesn't exist, right? Every gas deviates from the ideal gas law. So what we see is that as pressure increases, right, we're going to see deviations from the ideal gas law. So when we're looking at these graphs, we see that we have PV over nRT, right? You might be thinking, what does that mean? But remember, for an ideal gas, PV is equal to nRT. So PV over nRT is just 1. And so that's why we have a graph of 1 right here. And at any pressure, according to an ideal gas, this PV over nRT will be 1. However, looking at gases at different temperatures, right, we see that they deviate from the ideal gas law, right? So when do really gases differ from the ideal gas law, PV equals nRT? So there are two scenarios, right? High pressure. So at high pressure, gas molecules start to take up space, right? So the actual assumptions that they are a negligible distance from each other, it goes away, right? The kinetic molecular theory. So they start to take up space compared to the actual pressure, right? Because when pressure increases, remember, I think it's Charles's law, volume decreases, right? Or no, I think it's Boyle's, actually. Intermolecular forces will start to take effect. Right? When we're at a low temperature, we start slowing these molecules down, and suddenly they start feeling that attraction to each other, right? Because they have less energy to go flying around. So this is an equation that actually corrects for these two factors, and it's called the van der Waals equation. So really, this might freak you out. First of all, I'd like to say that you will never have to actually plug into this equation for AP chemistry. There will never be a situation on the AP exam where you'll be plugging into this. You just have to understand it, right? And thinking about this, remember, so this term has to do with the high pressure term, right? So when volume's really small, right, or when volume is actually negligibly large, this is going to approach zero. Similarly, with this, it'll also approach zero. And so for an ideal gas, PV is still equal to nRT. But for a non-ideal gas, PV is not equal to nRT. It's going to be slightly more or less. However, the ideal gas law is still really handy if we are at a regular pressure and a regular temperature, due to the fact that these terms will actually kind of cancel out, and they won't have as much of an effect on the end answer. So PV equals nRT is essentially a simplification of the van der Waals equation. Right, so here are a couple little things that have to do with it. So kind of looking at this, right, we see that those four molecules kind of get tightened in, right? I have to kind of restart the slide to get the actual animation to keep going. Right, it assumes that the space is available for all the molecules to move in. Excuse me. But only this amount of room is available because the rest is taken up by the molecules themselves, right? And that has to do with the actual deviations from the ideal gas law. Similarly, in a real gas, we see attractive forces that occur, right? We see, if we have water vapor, we're still going to see those hydrogen bonds happen. And so that's where the ideal gas law fails. So I know there was one person who was kind of iffy on it. So does it make better sense now, or do you still have a couple of questions on it? All right, looks like if we're okay, kind of keep going on. Right, so our next topic is mixtures and solutions, right? So the first thing we're going to learn is calculations involving molarity. So molarity is a measure of concentration. Basically, how much solute, right? How much stuff do we have dissolved in how much solution? So molarity is the most used one on the AP exam and in really chemistry in general. Molarity basically is moles per liter. If you have, for example, 4 moles of sodium chloride dissolved in 3 liters of solution, you have a 4/3 molar solution. So same thing here, right? If you have 3 moles of hydrochloric acid dissolved in 3 liters of water, you have a concentration of 1 molar, right? 3 moles per 3 liter, which is 1 mole per liter, which is 1 molar. And the notation for this isn't really relevant now, but it will be heavily relevant later, is when you see something in brackets, that means concentration. Specifically, it means molarity, right? So another application of molarity will be dilution, right? Decreasing concentration by adding water, right? It's always going to be water. And you want to use the equation M1V1 is equal to M2V2, right? And it makes sense because you need the moles of solute to remain the same. You're not adding any solute. And so you need the moles per liter times liter to equal the moles per liter times new liter, right? And so that's how dilution works. right? And it's pretty simple to understand when you need to use it, right? Just a change in molarity or a change in volume. All right, so the next thing is representations of solutions, right? So when we're looking at a solution, remember, there are going to be two things. There's the solvent and the solute, right? And the solvent dissolves the solute. So we see what actually happens is the solvent and the solute expand and form a solution, or they directly form a solution. But in the end, you end up with this form of a solution where you have the solute integrated in the solvent. And that's really the whole point of a solution, right? You have mixed thoroughly throughout. You have a homogeneous mixture, right? It's kind of a weird thing that if you're a visual person, it makes sense in terms of just kind of, it's trivial to visual people. And really, it is kind of simple in terms of, right, it makes sense. You have the solute dissolved in the solvent. Right, so now we're going to be talking about how do you separate a solution, right? If I have something dissolved in something else, or I have a solution of two liquids, for example, how do I actually separate them? So the first one is called distillation. So distillation takes advantage of boiling points and differences in vapor pressures in order to separate a solution. So this may look like a really complicated thing that's going on here, but really what's happening is we have a hot plate here, right? And what happens is we set it at a specific temperature to boil the lowest boiling of the two things in the solution, right? So for example, if you have, I don't know, two liquids, and we have one that boils at 70 degrees, one that boils at 1700, right? We set it at 70 degrees, and that first bit will start to dissolve, or will start to, not dissolve, will start to boil. And so it evaporates out of the solution, and it goes into this long tube labeled 5. So what happens is, when it goes into that tube, we use typically water to cool it down back into the liquid phase, and it's collected right here, right? So it's a pretty simple process at its base level. There's some really complicated distillations that I've seen, but really that's really the main point. You boil, you have different boiling points, so you boil one out is mainly the main point. The second one is called paper chromatography. So chromatography separates mixtures by taking advantage of polarity and non-polarity, right? So for example, when you have an ink spot, right, it's a mixture actually of a bunch of different inks. And so if you put a dot on paper, and you can do this at home, if you put a dot of ink on a little piece of paper and you dip it in water, the water will travel up the paper and pull the ink up the paper based on the polarity. Right, yeah. Most chem classes end up doing some sort of paper chromatography. I actually did in 8th grade. I didn't do it in AP Chem, but it's something that, yeah, a lot of people have been exposed to, right? It's relatively simple. Okay, so moving on, we're going to be talking about solubility, right? But it is kind of weird seeing the water go up, right? It kind of travels up. It's pretty interesting, though. Right, so solubility is just what it sounds like. So this looks like a lot of text thrown at you at once. The solubility rules that the AP test wants you to know specifically. Group 1A elements, nitrate and ammonium, are soluble. Those are the ones you really need to memorize. However, don't dwell on memorization. It becomes pretty clear what's soluble and what's not through usage, right? You can memorize your solubility rules if you really wanted to, but typically you learn what is and what isn't by just doing it. You learn that silver chloride is highly insoluble. You learn that silver nitrate is highly soluble. That sodium, that ammonium chloride is soluble, stuff like that. And the major thing to take out of this is that like dissolves like. A polar solvent will dissolve a polar solute, etc., etc. Right? So really, this is just a list of rules. Solubility has to do with basically how easily something can be dissolved. And you'll find later that technically everything is dissolved a little bit, but it's based on these rules basically show you what is dissolved a lot, right? What will actually dissolve in water to an extent that you can see it. All right, so moving on, we're going to be looking at the electromagnetic spectrum and the photoelectric effect. So kind of a big jump from what we were just talking about. So the electromagnetic spectrum, I think most of us have probably heard of it, right? It has to do with wavelengths of light, right? Remember, according to quantum theory, light is a wave, right? It has a particle wave duality, and based off of where a particle of light or wave of light exists on the electromagnetic spectrum is based off of its wavelength, right? And it goes gamma, X-ray, ultraviolet, visible, infrared, microwave, radio. I don't know if you actually have to memorize it. I don't think you do. But basically what it has to do with is high frequency, or short wavelength, suddenly to longer wavelength, right? Or lower frequency, right? And that's basically the trend across the electromagnetic spectrum. And we'll be looking at basically what it means to have a low frequency, a high frequency, stuff like that. So there are a few equations for light that you will need to know. So H is defined as Planck's constant, right? And it's 6.626 times 10 to the negative 34 joule seconds. So really what Planck's constant shows is that light is quantized, right? When you reach a little particle of light, energy will be released in quanta, little packets that are proportional to the frequency. So basically, this brings up the formula that the energy of a photon is equal to Planck's constant times mu, not mu, what is that? H nu, right? That's the Greek letter nu. That is the energy. Joule seconds is kind of a really weird unit. Kind of ignore the units in terms of their actual units. Just know that, think about it this way, right? Yeah, it's a little weird, right? So when we multiply joule seconds times, so the unit for frequency is per seconds, right? Basically, how many wavelengths do you see per second? And so you see the per seconds, cancel the seconds, and you're left with joules, right? So looking at this image, we see that, for example, when an electron moves down a couple energy levels, it releases a photon of light in the form of energy proportional to h times the frequency, right? So that's really where it comes from. And here's another image of it, right? That energy is emitted in quanta, right? Little packets of h nu, right? So E is equal to h nu. Yeah, the Balmer series is, I believe, from the second to the second energy level, I believe. So second of all, the speed of light can be defined by wavelength, that's that little Greek letter lambda, and nu. Right? We see that C is equal to lambda nu, where C is 3 times 10 to the 8th. So the units really do make this clear, right? Meters per second is equal to meters for the wavelength times per second for the frequency. So meters per second will give us the speed of light, which has been proved by Einstein to be a constant. Right? So basically just looking at those two equations. So the second part is looking at what's called the photoelectric effect. So essentially what the photoelectric effect is that when you blast a piece of metal with light, you sometimes see an electron pop off, right? You see it just go boom, boom, right? And the real problem was, and it was solved by Albert Einstein, it's actually the one thing he won a Nobel Prize for, was for solving the photoelectric effect, right? He figured out, yes, EV is different from joules. EV is electron volts. It is a measure of, I want to say power. An electron volt is a unit of energy, which is a much less than a joule, right? Because 1 electron volt it has a really scientific-y thing, but just note they're different from joules. So really what Einstein and other scientists and what other chemists and physicists had actually observed is that when you blast a piece of potassium or other metal with light, you see an electron sometimes pop off, sometimes not. So you kind of ask, okay, well, why, right? It's because when you add enough energy to it, you have to add enough energy to knock off an electron, right? To promote the electron all the way off of the metal. And so when you use something like red light, it does not have enough energy actually to knock off an electron. Whereas when you use something like green or purple light, you do knock off an electron. You can go into the physics of this and the quantum mechanics all day, but really the basic idea is just blast it with light, an electron is knocked off. So finally, the final thing we're going to be talking about tonight is Beer's law of absorption. So there's going to be a picture after this, but basically Beer's law can be summed up by the equation A is equal to ABC. The absorption, yes, there is a stream of, on this in 2 days, right? So the person's going to be going into this in much more detail, so I'm going to go through this kind of quickly. A is equal to ABC. Basically, the absorption is equal to the molar absorptivity, which is kind of a constant, times the path length, I'll explain what that is, times the concentration of a solute. So it's used to actually find concentrations. So it's used in a type of experiment called spectrophotometry, right? So for example, we did this lab last year in my chem class. You will find the concentration of red dye in Gatorade, right? So you blast it with green light, and you want to see how much green light will be absorbed, right? So here's a little picture that might make it clear, right? When you blast light through a solution, right, some of it's going to be absorbed, and then the rest is going to be transmitted. And so assuming a constant B, right, a constant path length, which is right here, this is the path length, right? We see that A is equal to M, or AB, times C. So we see a direct relationship between absorption and concentration. So I won't really go more into that because I know there is a stream on this, as Parth mentioned. So yeah. So that is Unit 3, right? At long last, we made it to the end. I'm going to chill out for another minute or two. Just, do you guys have any more questions? Anything else to mention? Questions, comments, concerns, right? I know I kind of blasted all the way through that material because there's a lot of it. So if you guys have anything that you're really confused on, feel free to ask right now, And if not, I think I'll just end up logging off. I'll hang out for another 30 seconds or so, see if you guys have any more questions. Good stream. It's gonna. Thank you. Yeah. Hopefully, feel free to share this with as many people as you can. Yeah, I'll be streaming. I mostly do the reviews, so like this type of stuff, the big hour-long mega reviews. But I'm happy to, if you guys want to do some problem videos or some other streams on random other topics. But yeah, I think on that note, I'm going to log off for the night. I will see you guys next time I stream, which will be sometime in the future. And I will talk to you guys later.